Okay, part 2 of the video, chapter 6, part 2, we're gonna go and talk about tension. So, force exerted by a rope or cable. And as you can see here, a force is being exerted on a box here. Now, if a rope or cable is massless, oh, that's a typo here, it should be L, massless, the tension is transmitted undiminished, okay? So if I have a massless rope here, all of the force that this guy is applying to the rope will be directly applied to this box through the tension of the rope. If the rope or cable passes over a massless, frictionless pulley, as you can see here in this picture, then the tension reaches the other end of the rope undiminished. In other words, this fixed pulley up here is only changing the direction of the force. So this guy is pulling the rope down with a tension or a force of T, and this tension or the force of T is being directly applied to this other end, and it has changed, the direction of it has changed. Obviously, as you can see here, the tension is downward because the force is down, but then this pulley, this fixed pulley, is changing the direction for us. And we have the direction of the tension upward or along the positive y direction because there is a fixed pulley, all right? If the rope is massless, then all of the tension that this guy is applying to the rope will be directly applied to the other end without being diminished, okay? So the ideal spring is the other part. Obey the Hooke's law, and the Hooke's law is F equals negative kx. K is the force or spring constant. It's a constant that usually is given, or the problem might ask for it, but it is a constant. And K is a force. K is a measure of how hard it is to compress or stretch a spring. The higher K means it's more difficult to compress or stretch a spring versus a very small K, which means that it is much easier to stretch a spring or compress it. X is a displacement, and it means how far the spring has been stretched or compressed from its equilibrium point. And F is referred to the restoring force of the spring, force needed to return the spring to its original length. So let's take a look at what we have here. So what I have, let's say that I have a spring kind of like that, okay? And it is at equilibrium at this point, and then with the constant of K. But then what I would do, I would try to stretch the spring a little bit, okay? So this means that the spring has been stretched for the amount of X, okay? So we just applied some force and stretched the spring, and the displacement is X. That means now there is a force stored in the spring, and it is in the opposite direction of the stretch all the time. So that is the F that we're talking about. And this F is negative KX, okay? X is the displacement that you can see here. K is the spring constant. And this negative, which is a little bit tricky, why is it negative? This negative means that X or displacement and force F are in two opposite direction. Okay, so in other words, I have a positive X direction here, and I have a negative X direction towards that. So this is positive X, this is negative X. So force is along the negative X direction. Okay, that's why we have a negative there. It means it is in the opposite direction of motion. Direction of the motion of the spring is always positive. All right, so Let's take a look at this one. This is a little bit more clear because it is a picture from the book. So Hooke's law, this restoring force of the spring, as we just talked about it, the f of x is negative kx, and k is the constant of the spring. The force exerted by the spring is negative because the opposite of the displacement. So you have a ball connected to a spring here. You are stretching the ball, okay? You are moving it from this point towards the positive x direction. Okay, so the displacement is this arrow that you can see on the screen, but the force is in the opposite direction of the displacement. So that's why you have a negative here. On the other hand, if you compress the spring, okay, so you're making the displacement of x to the left. So this is x to the left. And then the force is towards the right because it wants to bounce back towards the right. So the force and the x are in the negative direction. In this case, the positive x direction is here. So this is positive x direction, all right? And in this case, this is positive x direction, all right? So pay attention to this. The direction of displacement is always positive, and that's why you have a negative for force, because it's always in the opposite direction of displacement. The same stuff over here, all right? The same stuff over here. Now, next part of this chapter, definition of equilibrium, and this is also very important. I can guarantee you that you will have a problem be given to you in one of the exams about the equilibrium. So pay attention to this. This is extremely important, all right? Now, an object is in equilibrium when it has zero acceleration, okay? So in other words, if A is 0 meters per second. So, or what we refer to as statics, okay? Object does not have to be moving, all right, with a constant, it can't have a constant velocity. So acceleration of 0 has two meanings, right? One, the velocity is 0. The other one, velocity is a constant number for us. 5 meters per second, for example. Constant velocity of 10 meters per second, 5 meters per second, whatever, right? So if that is happening, that's one of the requirements is to have an equilibrium, either the constant velocity in our system or no velocity at all, or the velocity of 0. That means that A is 0. And what it means is that, remember this, total force acting on a system is ma. If A is 0, if this guy is 0, all right, what it means is that I am having a total force acting on this object being 0 when it has the equilibrium. Or in other words, the total force along the x direction should be 0, or the total force along the y direction should be 0. So this is the requirement to have the equilibrium. Total force along the x should be 0, total force along the y should be 0. So both of them are correct and should be both present to have the equilibrium. So the strategy is for Newton's first law and equilibrium. Sketch the physical situation. Always sketch a physical situation. It's an essential thing to do when you're dealing with physics problems. And draw a free body diagram for each object in the equilibrium. So do not include the surface it is resting on, or a rope that pulls it, anybody that's interacting with the object. So determine what is interacting with it and draw a force vector for each interaction. Label each force with a symbol that represents the magnitude of the force. We'll see in the example. And do not include any force exerted by the object or internal force. If you remember our chapter 5, I said do not include the internal force. All the internal forces are in pairs, they are action reactions, and they will cancel out. Okay, choose a set of coordinate axes and include them in your drawing. Okay, this is the overall strategy to solve these type of equilibrium problems. Okay, let's take a look. One-dimensional equilibrium along the y direction. Draw a free body diagram for each of the following situations. So what I have here in this top over there, let's draw it. It's already been drawn, but I mean, I wanted to make it a little bit better. So I have a mass of an object, or an object with mass m, and then what I have here is mg, downward mg, or w, okay? I have it right there, force by gravity or weight. And it's a force, so I can just put an arrow on top. So it's always towards the Earth center. And then we have another force being exerted by this guy, okay, with a hand, 11 newtons. So that is a F of 11 newtons being exerted by a hand. And then we have a normal force, because it is normal force because of the surface. So the normal force, normal to the surface with an angle of 90 degrees, or normal to the surface, which is N, okay? And all the forces along the y direction should cancel out. So sigma F along the y direction should be 0, because the object is not moving, there is no acceleration, so they should all cancel out. In other words, we have two forces that are downwards, right? One is 11 down, the other one is mg down, which is, by the way, given to us, which is 15 newtons here. So I'm just going to add it right there, right? And we have one upward normal force, so they should cancel out. In other words, the up should equal to 11 plus 15, or 26. Okay, so that's the requirements. Let's take a look at the second problem here. Let's take a look at the second problem. So in the second problem, what I have is, oh, that was too big. So in the second problem, right there, there we go. Okay, so what I have is, I have another box, and the other box is located there, and it has the same weight. So W, which is mg, which is 15 newtons, okay? And then I have a force of 11 newtons upward, because somebody's pulling it up with a rope. And then what I have is normal force. So I am going to show the normal force here as well. Normal force. Remember, sigma F, or all the forces along the y direction and x direction, should cancel out. By the way, I am going to add that here as well, because it's also true. So along the x direction should be 0. Now, over here, along the y direction, I have two forces that are up and one that is down. So the two up should cancel the one that is down. So I have normal force plus 11 equals 15. In other words, the normal force should be 4 newtons, okay? So this is how the equilibrium works. All the forces along x and y should cancel out. So let's take a look at this one-dimensional equilibrium. It's example number 3. So let's work on this problem. Suppose you have two blocks with weight W, okay? And consider the following situation. Determine the tension T in the rope in terms of the weight of the block. Now I'm gonna solve A and B, and you can work on part C. If you have any questions, let me know. So a single block is attached to a rope. The other end of the rope goes over a pulley and is attached to a wall. So in other words, what we have here is kind of looking like this. I have a block with mass of W, and it is attached to a pulley, and the other end is connected to a wall. So this is kind of where our wall is, okay? And then what we know is that we have, this is a mass M, the block of mass M, and this is W, the gravitational force exerted on the block by the Earth gravity, which is essentially mg. And then what we have is T, which is the tension in the rope, as you can see right there. So what we're looking for in this part is the tension T in the rope in terms of the weight. So now what you can see here is that you have a block, okay, which is here. So sigma f of x is 0, sigma f of y is 0. So in both directions, x and y. And so this is our x direction, okay, and this is our y direction. All right, so in y direction, we have T up, and we have mg or W down. So T is equals to mg if you have the equilibrium. All right, part B, the pulley is attached to the ceiling. 2 blocks are suspended from either end of the rope, which goes over the pulley. So in other words, we have, in the second part, we have something like this. So in part B, we have a ceiling or a wall, okay, and then we have a pulley like that. And then what we have is that we have one side of it is this block, the other one is this one. So let's call them block and M. They have the same mass. So we have W, which is mg here. We have W, which is mg here as well. Okay, and then we have T up, the tension. Remember, the tension, the pulley is just changing the direction of the tension. So if this object, these two objects, or this system stays at equilibrium, that means for each object we have the equilibrium. So for each object, I can write f of x, sigma f of x, and sigma f of y to be 0, okay? So if that's the case, along the y direction, I have tension upward, or along the positive y direction, and I have W or mg down, which in this case, they're all equal because they have to cancel out if we have a velocity of 0, or if the objects are moving with constant velocity. All right? So go and read part C and try to do part C yourself. I'm just going to leave an area here for you. So do part C at home. Okay? So holding up a picture, that's another example. A person is trying to judge whether a picture with a mass of 1.1 kilograms. So I already know the mass of the picture. It is 1.1 kilogram. All right, is properly positioned by temporarily pressing it against a wall. So we have an object being pressed to a wall, and the mass of the object is 1.1 kilogram. The pressing force is perpendicular to the wall, obviously, that's right. The coefficient of the static friction between the picture and the wall is 0.66. So mu s is already given to us, 0.66. So in other words, I have a wall, okay, so that's our wall. And then I have an object, which I just show it with this. Okay, that's our picture with a mass of m right there. All right. And what is the minimum amount of pressing force that must be used? So in other words, I am pressing this frame or this picture or this block with a force of F, and I'm looking to find it. So I'm just going to put a question mark here. And when you're looking at this, immediately you know that this is W, or this is the weight, or mg, gravitational force by gravity, right, by Earth. And then if this picture is moving, The only direction that this picture can move is along the negative y direction. So what I have is this W is along the direction of the motion if it's moving, okay? So that means that my force of friction, or F of S, is upward. I can understand that. The other force that we have is normal force. So this is normal force, F of N, or normal force. So I can, if it's at equilibrium, sigma F of X should be 0, and sigma F of Y should be 0, which means along the X direction, F should be equal to the normal force, or normal force and F should be equal, okay? If it's not moving along the Y direction, which means that F of S, or static friction max, or F of S here should be mg, okay? So max. And we know what F of max is. We already know the formula for it is mu s times n, okay? So mu s times n. So now if I want to write it down, I can substitute mg for F of S, okay? So in other words, I can write mg equals mu s dot n. How did I get that? I got it from here. So I just substitute this guy in here, okay? Now, let's go back to our formula. So mg is mu s dot n. Let's solve it for n. N is mg over mu s, right? We know what mg is. M is 1.1 kilogram, 1.1 kilogram times 1.1 times g, which is 9.81, over mu s, which is 0.66. Okay, now if that's the case, I can find m, and based on an easy calculations, I can find out what the value for n is. So it is 1.1 times 9.81 over 0.66, which is 16.35. So if you do that, n is 16.35 newtons. It's a normal force. And if you're looking at this, if you're looking at along the x direction, kind of like that, if you're looking at this guy, that means whatever F that you're applying, F is N. So your force should be 16.35 Newton, right? To keep the object from falling down. Okay, so let's take a look at this one. Exercise 5. So two-dimensional equilibrium. Now, you can have the two-dimensional equilibrium. It's the same idea of one-dimensional equilibrium. Remember, the forces along the x and along the y should cancel out. We have a car engine hangs from a several chains. Find expressions for a tension in each of the 3 chains in terms of W. Okay, so in other words, I have a massive object, or M here, and it is producing W equals mg for me, okay? And this means I have a T3 here, I have T1 here, and I have T2 here. So if this is staying in equilibrium, all of these T3, T2, and T1 should cancel out at this point. Otherwise, this point will start moving, okay? So T3, T2, and T1 should cancel out by default. So let me actually draw it a little bit better and a little bit more to scale, because I need to show where T1 is. So T1 is also here. All right, so what we have is a two-dimensional equilibrium, and we're looking for T1, T2, and T3 in terms of W or mg. All right, so let's take a look. I have a T3 here, all right, and I have a T2 here, and a T1 down here. So I have all of them. And then the other very interesting point here is that this angle is 60 degrees, okay? This angle is 60 degrees. If I continue this angle, if I can just show you what it means and what I mean by that, if I can continue this, okay, then I can show you that this angle is also 60 degrees, okay? Because if you have two parallel lines and you have one line that is going through them, making equal angles, so these two angles are the same, which is the exact same thing happening here. 60 degrees up there, 60 degrees down here. So I have, in other words, I have 60 degrees down here as well. So I have to define my coordinate system. If I want to define my coordinate system, the first thing I need to do is to show it like this. So I have my X and I have my Y. And so this is X direction and this is Y direction, all right? And this T of 3 or T3 has a X component. So this X component is, let me actually write it with another color. I'm using a lot of colors here. So this is T3X, and this is T3Y, all right? And we know what they are already. T3X is T3 cosine of 60, and T3Y is T3 sine of 60, okay? That's what they are. Okay, so let's write down the equilibrium. Sigma f of x should be 0, sigma f of y should be 0. Along the x direction, what do we have? Along the x direction, I have T3x equals T2, which means T3 sine of 60 equals T2, okay? Along the y direction, I have T3y equals T1, or T3, oh, this should be cosine. So let me actually write this one completely, and then I will go and change this. This should be cosine of 60 because this is along the x direction. I have it right there. So cosine of 60, okay? Now, if you do that, then you have shown your equilibrium equations along the x and y. Now, if you're looking at this engine is staying still, right? This engine is with a mass m with a weight of w or mg is staying at equilibrium as well. So for this object, we have to have equilibrium both along x and y direction. So for engine, okay, for engine, what we have w, which is mg, being equal to T1, okay? So if we do that, I can just substitute, whenever I see T1, I can just substitute as W, okay? So I can use this W and write it right there, okay? So in other words, I can write T3 sine of 60 being W, and therefore T3 is W over sine of 60. Okay, once you do that, now you have T3, then you can use this T3 and put it right there to find T2. So T3 cosine of 60 is T2. In other words, if you want to find T2, you have T3, which is W over sine of 60 times cosine of 60. And then your T2 is W times the cotangent of 60 degrees. So that's your T2. So you were able to identify both T3, T2, and T1. So you're right here. Okay. Let's take a look at this example. Example number 6, the Atwood machine. When two objects of unequal mass are hanging vertically over a frictionless pulley, so this pulley is frictionless, obviously, and of a negligible mass. So the mass, it is also considered to be massless. It's hypothetical, it's not real, but that's what we do in physics to understand the problem. And the arrangement is called the Atwood machine. Now you have obviously a massless rope as well connecting these two M1 and M2. And this is, by the way, one of the labs that we're supposed to do. The device is sometimes used in the laboratory, as I said, to measure the free fall acceleration G, determine the magnitude of the acceleration of the two objects, and the tension in the lightweight cord. So what we're looking for is to find the acceleration of this system, because we know if they move, they both move with the same acceleration. And we want to know the tension in the rope. So that's these two things that we're looking for. Okay. So let's say that M2 is greater than M1. As you can see here, the direction of the acceleration is showing that the system is moving clockwise. Okay, so that means that M2 is greater than M1 just because they are moving clockwise, and that's what it means. Okay, now if I want to write that down, I have to show that they are moving in the same direction. Now, so what I have here is I have M2G down, I have T up here, I have M1G down, I have T up there, okay? So let's write down sigma F equals MA for one of the objects. For example, for the first object. Okay, so for the first object, I have T minus M1G equals MA. And for the second object, for this one, for M2, I have M2G minus T equals MA. And this is M2, this is M1. Okay? They have the same acceleration. Right? It doesn't make sense to have two objects hanging and then have two different accelerations. If you have a tight rope here with a tension, then that means that both of these objects are tight and are moving at the same rate, moving with the same acceleration. So that's why I didn't use A1 and A2, and I'm just using A to show them. Okay, then and also we have one tension in the rope, otherwise the rope wouldn't be tight. So that's why I'm not using T1 and T2 here. I'm just using T. So right now I wrote a second law, motion law of Newton's second law of motion for both objects, for object 1 and object 2. Now when you're looking at this, you can kind of play with these two equations. There are two equations that are both valid, and you can find what you're looking for using these two equations. So if I do add them up, let's add them up. Let's see what would happen. So whatever that I have left-hand side of the of this equal sign, I have to add up. And then whatever I have on the right-hand side of the equation, I have to add them up as well. So if I do that, I will have t minus m1g plus m2g minus t equals m1a plus m2a. Okay, something that you can just easily identify is that you have a t plus t here and a negative t here. They will cancel out. Okay, and then now you are left with m2g minus m1g equals m1a plus m2a. All right, now go ahead and factor out this g here. So you have m2 minus m1g, and then factor out a. You have m1 plus m2a. So you can just easily find a, the acceleration, which is m2g, or m2 minus m1, m2 plus m1 times g. That's what it is. So this is the acceleration. So the first task is done. Boom. Okay, so all I did was to write the second law of Newton's second law, and then for both objects, and then I add the equations. They're valid, right? They're both valid. The left-hand side for each is equal to the right-hand side, so I can add them up. All right, so that's what it is. Now, in order to find the acceleration or the tension in the rope, what you need to do is to easily substitute this A. You can easily substitute this A back to one of these equations and solve T for it. Or in other words, if you want to write something else, let's actually have let's actually write down something like this. So to find tension T, what we need to do is to have these equations one more time. Let me actually scroll up a little bit so I can see them better. So I have T minus M1G equals M1A, and I have M2G minus T equals M2A. So that's what I have. I'm just going to write them down one more time. Okay, so now when you're looking at this, by the way, when you're looking at this, you want to get rid of this M1 or M2. So I am going to multiply the first equation by, let's see, I can multiply it by M2. Let's do that. Okay. And I can multiply this one by M1, this whole equation by M1. Okay. So what I have here is, let me actually change the color one more time to be consistent. Okay, so I have M2T minus M2 M1G equals M1A, and I have M1 M2G minus M1T equals M2 M1A, and I have an M2 here as well, right? Because I'm multiplying everything by M2. Now, if I add them up again, let's see what will I get. So if you add them up, you have this M1 M2G, this M1 M2G with a negative sign. They will cancel out. So you will left with M2T minus M1T equals 2M1 M2A. Okay, so you are left with m2 minus m1 t equals 2 m1 m2. You have a, right? That's what you have right there. So you have m2 minus m1 m2 plus m1 times g. Okay, so you can cancel out the same terms from left and right. So I have m2 m1 right there, m2 m1 right there, m2 minus m1. So right now what I am left with is t equals to 2 m1 m2 over m1 plus m2 times g. And that is the tension that you have in the rope for the Atwood machine. All right. So example number 7, pulley and friction example. So 3 objects are connected in the table as shown in the figure. To the right, the table is rough and has a coefficient of kinetic friction of 0.35, which is actually pretty high. So, so the coefficient of kinetic friction, mu k, is 0.35. The objects have masses of 4 kilograms, 1 kilogram, and 2 kilograms, as shown here, okay? And the pulleys are frictionless and massless, and the rope is also the same, massless, okay? Draw a free body diagram for each of the objects, okay? So let's do that first. I have a mg down here, okay? I have a tension of the rope right there, T, all right? Or I'm just gonna call it maybe T1, all right? And I have the same T1 over here. I have mg down here for this object. I have T2, tension of the rope, and T2 right there. Remember, these two different ropes are different, have different tensions because they are connected to a different mass. So that I can't call both of them T because they are not equal. Tension in this rope is being produced by mg, but the m is 4. Tension on the other side is being produced by an mg, which m is 2 kilograms. So T2 and T1 are not equal. This is very essential. T1 is not equal to T2. The other forces that I have here is I have mg for that object, for this particular object, and I have a normal force as well. Okay, so that's what we did. Draw a free body diagram for each object. Set up the equations for Newton's second law for each object. So the first thing that we need to know is to know in which direction these objects are moving. In other words, so if this is moving, in which direction it's moving. All right. So what I have here is I have these are all internal forces. So the tension will cancel out for T1. We'll do the same thing for T2. If you consider this as a whole system, in one system with one acceleration, the internal forces will cancel out. N and mg will also cancel out. So which side is having the more stronger pull, or which side is applying with more gravity? It's all obviously this side. So the direction of motion is counterclockwise, okay? So this is the direction of motion, right? Now, if this is the direction of motion, that means that our object on the table will move towards the left. And in other words, I have the kinetic friction right there in the opposite direction of motion. It's a friction causing the object to slow down. So that's what we did. Now let's go ahead and write the second law, Newton's second law. So sigma F equals ma, that's what it is, right? So let's see what we have. So if they are moving counterclockwise, okay, and all the internal forces will cancel out, as we said, or all the forces that are caused by the objects will cancel out. What are we left with? We have mg down here. we have these T's will cancel out, they are internal. All the forces along the y direction will cancel out, so N and mg will cancel out. I have over here T2, which will cancel out because they're internal forces. And then I am over here having an mg with m of 2 kilograms, and then of course a f of k. So I have mg minus f of k minus mg, but this is 4 kilograms. So this is 4 kilograms. And this is 2 kilograms. Well, I have to know that, right? And equals ma, and this is m4 plus m1 plus m2. That's what it is, right? Because they are all moving, so the total m is there, and it's not only one m, it's 3 m's, because we have all the different forces from all of them, so we have to include all the masses here. Now, let's put some numbers here. So I have m2g. Let's actually play with it a little bit more. F of k is mu k dot n minus m2g equals m4 plus m1 plus m2 times a. And we know what n is, right? All the forces along the y direction will cancel out. That's the rule. So n is m1g, right? So I can just use that and put this guy right there, okay? So I have m2g minus mu k, m1g minus m2g equals m4 plus m1 plus m2 times a. So if that's the case, now let's put some numbers in. M2 is 4 kilo. Oh, actually, this is M4. Okay, so correction. This is M4, not M2. This is M4. Right, so this is 4. This is 4. Again, see, you have to go back and check your solution. This is very important. It happens to me. It happens to almost everybody. So M4 is 4 kilograms. G is 9.81 minus mu k. It's given 0.35, right? So 0.35 times M1, which is 1 kilograms, times G, which is 9.81, minus M2, which is 2 kilograms. G is 9.81. M1 plus M2 plus M3, M4 plus M1 plus M2. So M4 is 4, M1 is 1, M2 is 2 times A. Okay, so you can kind of put this in the calculator and solve it for A. Then you can find what A is, all right? Super easy. So we found A, and let's actually do that because this is a very interesting problem. So I'm gonna put this in the calculator to see what I get. So on the left-hand side, I got 16 point, let's say 2. It's actually 0.18, but I'm going to call it 2. 16.2. On the right-hand side, I have 4 plus 1, which is 5, plus 2, it's 7. So 7 times A. I can find A easily. A is 16.2 over 7. So if I do that, I will get 2.31 meters per second as the acceleration of the system. Now, if that's the case for the whole system, I can apply this acceleration to each object individually. But for example, I can apply it to this object, right? The Newton's second law for the 4 kilogram object. So I can find the tension afterwards. So to find T2 and T1, what we do is to apply the same Newton's second law to each object. So I have M4G minus T2 equals M4A, right? So M4 is 4 kilograms, G is 9.81, T2 is not given, we're looking for it. M4 is 4, and A is 2.31. Okay, so let's go ahead and calculate this to see what we can get. And I have 4 times 9.81 minus 4 times 2.31, and it is 30. Okay, let's do it one more time. So I have 4 times 9.81 minus 4 times 2.31 equals T2. So T2 then is 4 9.81 minus 2.31, which is 30 newtons for T2. For T1, we will do the same thing, but this time I am applying it to this object. Or this should be T1. So this should be T1. This is actually T1. So T1. That's just the naming. It doesn't matter what you call it, but we want to be consistent with our original, original drawing. So T1 is 30. And I mean this tension in this part of the rope. You can call it whatever, okay? And so for T2, let's do T2. I'm going to use another color because it's all red. It might be a little bit difficult to see. So again, sigma F equals MA. And it's moving counterclockwise. So I have T2 minus M2G equals M2A. So T2 minus M2G equals, let's actually put numbers. Why are we writing them again? So T2 minus M2 is 2 kilograms, G is 9.81, equals M2, which is 2 kilogram, A is 2.31 here, right? 2.31. And then that means T2 is 9.81 plus 2.31. If you do that, and let's put it in the calculator to see what we can get, 9.81 plus 2.31 times 2 is 24.24. So T2 is 24.24 newtons. Okay. All right. This is the end of part 2 of this video. We'll continue with part 3 right after this.